In this video, I will be talking about the very interesting subject of artificial neural networks and deep learning. This is two terms which I'm sure is familiar to you if you are watching this video. This is something which is talked about a lot in social media and mass media. It's very popular topics discussed everywhere. Unfortunately, there is a lot of confusion around about what neural networks actually are. And I hope that after watching these videos, it will be at least somewhat more clear to you what a neural network is and how that relates to deep learning. The agenda for the video is to give an introduction to these topics, talk a little bit about how we actually train a neural network, different types of neural networks, and also different applications of neural networks. In the previous video, which is about the introduction to machine learning in general, we talked about how it's possible to see machine learning as a framework for acquiring knowledge. Indeed, the reason we call it learning is because that's what machine learning does. It acquires knowledge from data. And this knowledge that we extract from data is encoded in some kind of model structure. And neural network is simply one such model structure which can be used to encode knowledge that we extract from the data. There is of course nothing magic to this procedure, as we have discussed in the introduction video. In order to do machine learning to any data set, you have to be sure that the information or the knowledge that you're trying to extract is in the data to begin with, and you really do need to understand the application you're working on. You have to know that the knowledge you're looking for is in the data and how to extract that knowledge from your actual physical system. There are some interesting observations to be made about the methods that we typically call machine learning. As I'm sure you are aware, there is other techniques of data-driven modeling which is not typically named as part of the machine learning sphere. One such example is the system identification techniques, which is used a lot in engineering for dynamic systems. But also the field of chemometrics, which is sort of a multivariate data analysis based on principal component analysis or partial least squares regression. This is also data-driven modeling techniques, but they are not typically used or lumped together with the field of machine learning. And there are some typical properties of the methods that we do call machine learning. And from my observation, one of those properties is that there seems to be a certain freedom in the design of machine learning techniques. When we develop a new machine learning method, the basis of those methods tends to be relatively simple mathematical concepts, which is sort of combined together into complex structures. And this is different from these techniques of system identification or chemometrics, where we have rather a complex theoretical derivation as the basis of the method. And in machine learning, we sort of flip this around and we say that we have relatively simple model structures, but we have complex implementations, which makes the models work. In the other traditional methods like PCA or SID, there is a lot of theoretical derivation, which then makes the implementation simple. So it's two different ways of approaching this problem of extracting knowledge from data, which is data-driven modeling is all about. Another thing is that, or as an extension of this, I guess, is that because machine learning is based on simple mathematical concepts connected together into complex structures, what we end up is complex nonlinear model structures, which has a lot of what we call description power. That is, they have a lot of or strong ability to adapt to complex patterns in the data. Whereas the traditional methods tends to be based on linear model structures, which is an outcome of this theoretical simplification of the estimation problems. And then in machine learning, we then use the software implementation of the computer science to make these complex structures work. What is actually then artificial neural networks? Well, of course, this is a very important topic in machine learning. Artificial neural networks is probably the most famous of all the machine learning methods. Certainly one of the ones that's most talked about, both in industry and in society in general. It's gained a lot of popular interest in recent years, and it is indeed a very powerful type of model structure that can be used for a lot of interesting applications. It's by far the only model structure in machine learning. There is many others which tends to be neglected, at least by novices of the field. There will be other videos covering those. But neural networks is a very large topic, so for the purpose of this video there is no way I can cover the whole field in depth. Instead, I will try in this video to give an overview of the field, which I hope will help you to sort of understand the complexity of neural networks, at least get a basic understanding of what this is all about. And also I hope the video will help to navigate the field so that you can start exploring neural networks on your own. I believe very strongly that machine learning in general, and of course by extension neural networks, is a very practical hands-on subject. It's necessary to sort of get your hands on the keyboard and start doing machine learning in order to really get good, really understand what neural networks do. To start out, I want to explain a little bit what neural networks and deep learning has to do with each other. I'm borrowing a figure from deeplearningbook.org, which shows that artificial intelligence is sort of the overall field that we are operating in, and that machine learning is a subset of that field. This is kind of natural because being able to learn is sort of a prerequisite of being intelligent. It's a trait which is usually ascribed to some intelligence, that you can learn things. So it's natural to think of machine learning as part of artificial intelligence field. And in that sense, neural networks is a subset of methods that belongs to machine learning field. We mentioned already how machine learning is about extracting knowledge and coding that into model structures, of which neural networks is one specific type. Deep learning then is kind of a specific subset of neural networks again. It's a way to configure neural networks, which makes them particularly suitable for complex tasks, and we will show in more depth what that means. So an artificial neural network, as the name implies, is a network of neurons. And already from the name here, there's two things I want to call your attention to. First of all, we call this artificial, and that's because this is not really trying to copy how nature operates. It's inspired by nature, as we discussed previously, typical for machine learning methods. But it's not really a simulation of biological neurons in any way, it's just inspired by them. More importantly, however, we call it networks for a reason, and that sort of hints that network or structure is a key element to how we build neural networks. And indeed, the neurons by themselves is a very simple mathematical construct. It doesn't really do anything interesting on its own. This is also similar to how neurons work in biology. A single biological neuron is also not capable of doing a lot of interesting things. It's when you connect these things together into a structure that interesting things start to happen. And that is indeed true also of the artificial neural networks. So the first construct which we need to discuss is when we connect neurons together into layers. And this is an example of something called a feed-forward neural network, which is the easiest or the simplest neural network structure that we use. It's still a very powerful and much used network structure, even in the most modern deep learning applications. But it is the easiest to start with to understand how you can combine these neurons into a structure or a network. And the way this feed-forward structure works is that we have neurons stacked together into layers, and then layers stacked on top of each other. And at each connection between layers, we have the output of each neuron becoming the input of each neuron in the next layer. So each neuron has an output which goes to the input for each of the neurons in the next layer. So notice that all of the neurons have the same inputs, which happen to be the outputs of the previous layer. We will get back to the structure in a second, but first I want to show exactly what is a neuron in the artificial neural network sense. I mentioned already that it's a very simple computational unit, and what I mean by that is actually this little mathematical function here. So what the neuron actually does is it has some inputs, which I have called here x1, x2, x3. It can be any number of inputs, not just 3. It can be 1, 2, or 1,000. We don't know. It depends on the application. And it has some parameters, which is called training weights, which we denominate here W1, 2, and 3. And in addition, it has a special kind of parameter or training weight here, which we call the bias B. And the only thing a neuron really does is take the weighted sum over its inputs. So it takes input x1 times training weight w1, input x2 times training weight w2, input x3 times w3, and then adds all of that together as a weighted sum. And then we add this bias here. And that gives us the weighted sum over the whole inputs. And then one important detail is that we apply something called an activation function. I've said repeatedly that one of the keys to making machine learning and neural networks work is their nonlinearity. And if we neglect this activation function, this thing here would simply become something we call multivariate linear regression. So it would be a linear system and therefore not that capable of learning these complex structures. And this nonlinearity is key, as we will see in later slides. But for now, let's concentrate on this weighted sum. So we can do some mathematical trickery here, and we can just rename this bias parameter as a W0. And then we can pretend that we have an artificial input, x0, which always has the value 1. And then we see that x0 times w0 will just be b here. And by this little trick, we can then reformulate this sum over the inputs as a vector product, like this. So we have then w0, w1, w2, w3 stacked into a vector, multiplied by the input vector x0, x1, x2, x3. And mathematically, these are equivalent. So that's nothing new has happened here. It's exactly the same expression. It's just reformulated a little bit. The reason for doing that is when we think back to the previous slide where we had these layers of neurons. We remember that all of the neurons in the layer had exactly the same inputs. There was the same inputs going to each neuron. So the x vector for each neuron is the same. But the training weights are not the same. So each neuron has its own set of training parameters. So now we will take all of the training parameters for each neuron in one layer and stack those on top of each other into a matrix, which we call the weighting matrix W. And then we can express this whole layer of neurons as a very simple mathematical function like this. We still, of course, have the activation function, which we will see in the next slide what that is. But this is kind of interesting, that something which seems rather complex, a neural network, can be actually expressed as a simple matrix function like this, or in this case a layer of neurons. But we can take this further also to show the whole network structure. Because we said in the previous slide that we have the outputs of one layer becomes the inputs of the next layer, which means that we can chain this type of equations together. So here we have the inputs to the whole network, which is this x vector, multiplied by the weighting matrix of the first layer, and then the activation function of the first layer, And what we have out of this one is just the outputs of the first layer, which then becomes the input of the second layer. And the way we express that is that we just multiply by the weighting matrix for the second layer, like here. And then we apply activation function of the second layer to get output of second layer, then the third layer and the output layer. So actually here, what we have is a neural network, or a fully connected feed-forward neural network of 4 layers, which can be expressed as a simple linear algebra nonlinear matrix function. And this is kind of a light bulb moment when you understand that this complex idea, or what seems like a complex idea of neural networks, can really be expressed as a simple mathematical expression like this. And it really, I think, helps to understand that there is nothing magic with neural networks. It is a mathematical function like this, which has some very interesting properties, as we will see in a couple of slides. But first, a bit about these activation functions. So, just going back here, if we imagine that all of these activation functions were gone, we would just have a bunch of weighting matrices multiplied together, and then finally the input to the overall structure, which is basically just linear regression. So that's useful in some cases, but it's nowhere near the power of neural networks. So these activation functions, they are critical to making neural networks work. And there are a lot of different formulations of activation functions. The earliest one was this guy over here, which we call the perceptron. That's actually just the sign operator. So the activation function has the value -1 if the weighted sum is negative, and it has the value +1 if the weighted sum is positive. Now that's clearly a nonlinear operation, and therefore it helps to make the neural network behave as a nonlinear function. But it's not so much used anymore. We have other alternatives which are better than this. One alternative could be to actually have a linear activation function, which means that the output is just the weighted sum. Of course, if all of your layers have linear activation functions, it's like having no activation functions, and then we are back to linear regression again. So it's also not so interesting, but there are examples of using linear activation functions in some of the layers. The more typical activation functions is these guys here, the hyperbolic tangents, or the logistic sigmoid function. And this is clearly this nonlinear transition functions, which is typical of neural networks, where you go from -1 to 1 over this weighted sum, and there is some transition region in the middle where this is sort of almost linear, and then there is a region where it's clearly not linear. And the logistic sigmoid is almost the same, except that it goes from 0 to 1, and then outputs 0.5 when the weighted sum is 0, whereas this one outputs 0 when the weighted sum is 0. So they are similar. It's also interesting to note that these activation functions, there is a lot of research going into this as well. And one outcome of that, which is fairly recent, not that recent, I guess, in machine learning terms, it's 10 years ago, but the so-called rectified linear unit, which is used now a lot in deep learning. I think a few years ago it was argued that this is the most used activation function in deep learning projects. It was actually first published back in 1960, as a lot of the interesting things in machine learning, or I should say what we tend to think of as novel ideas in machine learning, a lot of those are actually traceable back to the 50s and 60s. There was a lot of interesting things going on back then too. But they really became popular around 2011. It was sort of rediscovered in a sense. This is a very simple activation function, which just outputs the weighted sum if that weighted sum happens to be positive. If the weighted sum is negative, then it outputs 0. And you can look up online to see that there are some theoretical discussions on why this is powerful. It has something to do with vanishing gradient problems when you train neural networks, that this type of activation function has some interesting properties in that regard. But the point here is just to show that something which is clearly very simple was only about 10 years ago that was really came into popularity in the field. So then to this other sort of half of the topic of this video, which is deep learning. But actually I cheated a bit, and I already showed you an example of deep learning. I mentioned initially that deep learning is kind of just a way of using artificial neural networks. And really what the word comes from is simply referring to neural networks where there is a lot of hidden layers. Initially it was like when neural networks were first sort of started to be developed, it was common to have just one hidden layer. But then when computers became more powerful, we discovered that having multiple hidden layers turned out to be a very efficient or very powerful model structure for machine learning. And that's where the term deep learning comes from, simply that there is multiple layers stacked on top of each other. So that's the deep direction. And this equation here, what I showed already, has 3 hidden layers, 1, 2, 3. So that is actually a deep learning neural network. It's nothing more magical than this. But of course, the more layers you have, the more complex your model structure, many more coefficients to train. You can see by this figure here, which is not that complex of a neural network for a deep learning. I mean, there's examples of deep learnings which are hundreds of levels deep with thousands of neurons in each layer. But this is still, if you remember from the previous slide, that each of these connections has its own parameter to be trained. There is a lot of blue lines here, which sort of shows that there is a lot of coefficients to train, even for something as simple as this. And this idea of having a model structure with a lot of coefficients, that's what gives neural networks their description power, that there is a lot of flexibility in the model structure in order to help it to adapt to complex interactions between our data. So neural networks, just like everything in machine learning, is not magic, even though it might seem like that, especially if you pay attention to mass and social media. People who don't understand machine learning tend to think that it is magic. It isn't. It's just simple algorithms that do exactly one thing, which happens to be very useful. And the same is true for deep learning. There is nothing magic about that. It's very well understood how these things work. There is a lot of research going into this, in developing the field further. And it's a very practical, hands-on discipline, an interesting field to work in for sure. So the question is then, if deep learning is just a bunch of neurons stacked on top of each other into multiple layers, why does actually this model structure turn out to be so powerful? I mean, it can do things, it can solve problems which doesn't have solutions in any other framework, like, for example, object recognition in images. People were trying for decades to come up with algorithms that could look at an image and understand the contents of that image, something which for us humans is very simple to do. It was really, really hard for computers until we came up with the deep learning frameworks. And now it's sort of something that anyone can do with a few lines of Python code. You can make your own object recognition thing with a web camera. Very simple to do now. So it's interesting to look at why this deep learning thing, this structure of multiple layers stacked on top of each other, works so well. And this sort of most obvious thing to note here is a phenomenon which we call abstraction. You can imagine that if you are looking at a bunch of pixels in an image, it can be very difficult to come up with a set of rules that from those pixels can calculate what those pixels represent, if this is a car, person or an animal. Instead, it makes sense to do some sort of feature extraction. So we look at the pixels and we try to recover something like edges, for example, so lines in the image. And that is what this abstraction effect does. It takes from the pixels and it comes up with something which is just slightly more explanatory than the pixels themselves. But then we can apply this abstraction idea again, and we can go from these edges into corners, contours, sort of frames around things, slightly more complex shapes. And then we can again go from these corners, contours into object parts, like here. And once we have object parts, then we can sort of from there classify what the contents of this image might be. I mean, if the image contains a wheel, it's reasonable that this might be a car. And that's kind of the key to why these deep learning structures are so powerful, that they can represent this abstraction effect by having this layered structure. So the first layer goes from pixels to something like edges, and then the second layer goes from edges to corners and contours and so on, all the way to the output. But it's very important to understand that this is something that happens naturally. It's not something that we build into the network. It's something that, because of how this network structure is constructed, it allows this effect to happen naturally. And it's simply the training algorithms' search for optimality that makes this abstraction happen. And in this example, we have shown the abstraction into things which make sense for a human. And that's not always guaranteed to happen. I mean, the computer in its training algorithms might end up abstracting into something which to us wouldn't make much sense, but still is an abstraction effect. So I want to also make a point on this idea of model complexity or description power. So I mentioned now that one of the reasons why neural networks is so powerful is their description power, their complexity, and their large number of training coefficients, which allows the structure to learn complex patterns in data. And this idea of model complexity giving description power is not, of course, unique to neural networks. That happens in all data-driven modeling approaches. So by adding more layers, we increase the description power of the network. And we can see that the same thing happens, for example, in something as simple as curve fitting. So in this example here, let's say that we have these black dots which represents data points, and we wish to fit some kind of polynomial to model how these data points behave. So here is a simple 2D space, x and y, and we want to create a model that can calculate y from x. So we could try to do that with a simple straight line. That's a model with just two parameters, y equal to ax plus b. And that would give us something like this red line here, which is not an entirely ridiculous model. I mean, it does sort of represent the general trend that these data points is going downwards, but it's clearly not a good match for the data points we have. And just by human intuition, we understand that having a straight line is never going to be able to represent these data points because there is some sort of curvature going on here. So we might want to try with a slightly more complex model. We add one parameter to go to a second order polynomial with 3 parameters. So we add one parameter, we get more description power, we can represent more complex patterns. And we see that immediately we have a much better fit to the data points. But it still isn't quite satisfactory yet. So we might need to add 1 or 2 more parameters to increase our model complexity and therefore our description power. And then we end up with a 3rd or 4th order polynomial, which is these blue and purple lines here. And we see that now our model fit is already quite good. And that's exactly the same thing what happens to neural networks, that we, by increasing the complexity, by adding more parameters, we make the model structure more flexible, more capable of representing complex patterns in data. So based on this, it's interesting to ask the question why neural networks became so popular in the recent years, let's say 10, 15 years. And the simple answer to that is the availability of computational power. If you have a model structure not like these polynomials which has 3, 4, 5 parameters, but you have a very complex neural network, a deep learning structure where you have thousands, maybe millions of parameters. Trying to identify all of those parameters in some sort of optimal sense is going to be a very computationally intensive problem. Training neural networks in general, as we will see in a few slides, is actually a very hard problem to solve. And because it is computationally expensive to actually fit a neural network to a particular set of data, it took a lot of time for hardware capability to catch up to the theory and the science which was already out there since the 60s. But once we had computers cheaply available that were able to store enough data and compute these things fast enough to be useful, then this field sort of exploded. So a little bit about the research front of neural networks. There's a lot I could cover here because there's a lot of research going on. It's an extremely active research field. And some of the things which is being researched is different network structures. It's almost on a monthly basis or even more often than that. New articles representing or presenting new types of neural network structures. We discussed already the feed-forward, which is sort of the original one. Some years ago we came up with the recurrent network structure, which I will discuss in a later slide. There's also something called convolutional neural networks. Another more exotic one is the pulse-coupled neural networks. There's a lot of these things. And I will, in the later slides, I will cover some of the more sort of predominant ones. There's a lot of innovation here. We mentioned already the rectified linear unit from 2011. By 2017, it was already the most popular activation function in deep learning. It's a fairly recent invention. There is other interesting things like the dropout, which is kind of a regression technique. So if you have these complex neural networks, as we mentioned in the introduction to machine learning video, one of the problems with machine learning because of the complexity in the model structures is this phenomenon of overfitting. And one way to combat overfitting is using regression techniques. And dropout and also drop connect here is two examples of regression regularization techniques that's applied in neural networks. It's also relatively recent inventions. Another interesting recent invention is the residual networks, which was proposed in 2016, and also the differential neural network, which was proposed in 2020. This last one is kind of a different use case of neural networks, where instead of trying to model the inputs X to the outputs Y directly, we have some sort of dynamic system behavior, and we want to use this neural network as a representation of an ordinary differential equation. So we try to model not the relationship between input and output, but we try to model the state transition of a dynamic system. So it shows the innovation in neural networks, that people are trying to use neural networks for almost anything, and it's a very, very active and interesting research field. So in this segment, I will talk about how to train a neural network. There's many terms for this. Some literature use the term calibrate, identify parameters and so on, but the most typical word in the machine learning is training. And very briefly, the training of a neural network refers to the process of actually learning with the neural network. So as we have seen in the introduction video, we have some data which we wish to model, and we will do that using the neural network model structure to encode the knowledge that we learn. And this segment will explain exactly how that happens, what is actually involved in training a neural network. So the first thing that I want to make very clear is that training neural network, as well as any, or at least most machine learning techniques, doesn't really have a global solution. If you're familiar with numerical optimization in general, which I will get back to in a couple of slides, you know that looking for an optimum, usually we are searching for something we call a global optimum, which is the best solution within some confined space. But because, as we said previously, machine learning methods, as well as neural networks specifically, doesn't really have a theoretical basis and are very, very complex model structures, finding some sort of global optimum for the parameters is in general completely infeasible. In fact, the training space, the parameter space of a model tends to look not like this exactly, but this is just an illustration to show something where it is very difficult to imagine trying to find the optimum in something like this. You see, there is many optimums, it's many minima all around this space. So trying to optimize in a space which looks like this is very, very difficult to do. And in general, neural networks or machine learning methods sort of give up the idea of trying to find a global optimal solution when we do training. We do have to account for local minima, and we have to try to make training algorithms that are to some degree resistant to local minima. Otherwise, we would just completely fail to train anything. But being able to find the globally best possible solution is generally not possible. So therefore, we expect that when we retrain this neural network on the same data, if we have a different starting point, a different randomized initial set of training parameters, we might end up with a completely different final solution and therefore a different performance. So when we do experiments, it's very common to account for this by setting the seed of the random number generator to a constant, so that we avoid this effect that every time we retrain the neural network we get a different result. And the reason that happens is because we have a landscape which looks something like this, with a lot of local minima. And some of them can be neglected because they are a very shallow local minima, and the algorithms are able to work around it. But nevertheless, the idea that there is one perfect solution for our neural network training algorithm, that's something we have to give up because of the complexity of the model structures that we work on. So in general, what we do is we search for something which is good enough. We try a lot of different parameter settings, and we search for a model which is has adequate performance for what we are trying to do. Now, because of this complexity, neural networks usually, or for anything but the most simple and uninteresting networks, require specialized training algorithms. If you just plug a neural network into a standard numerical optimization tool, the tool will probably just not work because it's too hard to find parameters in the neural network unless you do some sort of adaptations of your optimization method. The search space, of course, is very large. An optimization problem, the search space is the number of free parameters that you want to adjust. We saw previously that even the simplest neural networks has a very large number of parameters, and therefore very high dimensional parameter space to navigate. So something like 1,000 to 1,000,000 parameters is common. And then you don't have this structure here, which is like two-dimensional and still looks quite horrible to try to optimize, but you can imagine something like this, but in 1,000,000 dimensions. It's easy to understand that looking for a global optima in something like that is unfeasible. Just to say something about this idea of optimizing parameters in general, so then it's not really just for neural networks, but just parameter optimization in any kind of model structure. For those of you who are not familiar with numerical optimization already. The way we do that is that we define something we call an error function or an objective function. And that is some mathematical construct which says something about how good a specific set of parameters, or in the case of neural network, training weights actually are. And typically this is expressed like an error between some measured value, something that we have recovered from our actual system, and a predicted value, something which is generated by the model that we are trying to train. And then this error says something about the current state of the parameters that we have, how good they actually are. And then based on that information, the algorithm, the training algorithm, will make adjustments to the parameters in order to try to improve this error function j. So we want to minimize the error, for example, or optimize the performance. The sort of typical way of looking at this is what we call the gradient descent. So we have an error function, let's say, which looks something like this. That would be an extremely well-behaved error function, which has a very clear defined minima. And then we want to sort of navigate in this space, trying to find this point. So we start some random location in this W space. We can calculate j like this or in some other way. And then we want to sort of jump around and navigate and try to find this point. And clearly it's very useful if we know the derivative of this error function, because then based on one point we can say if the error function is going up or down, or something about the gradient of it, if it's flat. So clearly if we are here and the gradient sort of points this way, then we should move in that direction here. If you are over here, the gradient is pointing sort of down there, then we should go to the left. So that's just a very simple example to show that we in general would like to know the gradient of this error function in order to make this search for the minima more efficient. So as a very simple simulation of how that would look like, let's say we, by some random choice, a random number generator, start with a W1 here, this is our completely arbitrary starting point. We can calculate the j function, and we can calculate the derivative of j with respect to the parameter space, and we see that this is pointing in that direction. So beyond the initial random starting point, we then use our algorithm to suggest a new parameter which might end up over here, and again we calculate the gradient, which shows that we should actually move in this direction still, so we go further to the right. Here, again, another step. Still the gradient is pointing to the right. But now for some inexplicable reason, the algorithm decided that we should move very far to the right, so we end up over here. And now we see that the gradient is pointing in the other direction. So that tells us that we moved too far. And therefore, in the fifth solution, maybe we jump here. And now the algorithm will see that the gradient is more or less flat, which indicates that we are at the minima. As you know, the definition of a minima is something that the gradient is 0, or indeed any extrema point. And now we can say that the algorithm has converged. We found the minima, and we found that the optimal value for W in this case is here. That's the sort of the basics of all numerical optimization methods, is sort of this gradient descent, that we go down this error or objective function in the direction of the gradient. Now, these error functions is of course a very important topic in all machine learning, in neural networks also. And there is also research being done. How do we actually formulate error functions that are efficient to work with? One common example would be the root mean square error, or not necessarily the root mean, but let's say the square error. Sometimes we call this the sum of square errors. I'm sure this is familiar to most of you who have engineering background. You will have seen something like this before, where we basically take the error over all of our output measurements, we square the error and then sum it up to create this j function. Sometimes we take the mean by dividing this by n, and sometimes we take the square root of that again, depending on what we are looking for. Other interesting error functions, I don't want to go too much into detail here, but just to mention some of the things I think you should be aware of. So another interesting thing is something called entropy, which is a measure of how similar samples into different datasets are. So let's say you wish to classify or separate, classify two types of points. You have A and B, for example, and then you want to sort of draw a line in your data space between A and B. One way to figure out where to draw that line would be to look at the entropy. So you want a model to separate the data so that the two parts of data is as similar as possible, which would be can be described by this entropy function. Now, a couple of slides ago, we emphasized the importance of knowing the derivative. That seems very straightforward for the simple example that we presented. But unfortunately, the more complex model structures we have, the harder it is to obtain the derivative. And one of the really sort of breakthroughs of neural networks was the invention of this so-called backpropagation algorithm, which was the discovery of how we can actually obtain the gradient of a neural network. That is sort of a key challenge in all complex model structures, to find this gradient function with respect to the parameters. If you look at this equation here, you will remember this from the previous slides. It's just a little bit different notation. But when we have something where we have the input x multiplied by weighting matrix, and then the activation functions, and then stacked all of these layers together, that can be described as a function like this. And the basic understanding of the backpropagation algorithm is that we can take the derivative of this function here with respect to the parameters, sort of layer by layer, simply by using the chain rule of the derivative. So we take the derivative of this thing, it's going to be the chain rule applied to each layer. And then we take the transpose of these derivatives, which also, as you may know, when you take the transpose of the derivative, it also reverses the order, which is actually why we call this backpropagation, because we take the gradient of the last layer and then we propagate the error backwards through the network. So by resolving this gradient function from the output layer and backwards towards the inputs, we can actually obtain the gradient at each of these hidden layers. And this backpropagation algorithm was named not so long ago one of the 10 most influential algorithms ever invented, for this very specific reason, that it's a very elegant solution to this problem of finding the gradients, that is the gradient of the error function with respect to the parameters in a neural network. One other very important topic when it comes to training neural networks, which is perhaps of more practical importance than backpropagation. Most of you will never have to implement the backpropagation algorithm yourselves. In fact, I would strongly discourage trying to do so. It's very difficult to do that in an efficient way. It's much better to use the frameworks that's already out there. But one thing which is of practical importance is how do we treat our data sets in order to perform this training efficiently. And one very common recommendation is to divide our data into 3 different sets, which is commonly known as training data, validation data, and test data. Because in any sort of machine learning approach, and especially in neural networks, we will always have this training or calibration step, which we just talked about, which is the numerical optimization of the training weights, trying to obtain some sort of locally optimal parameter set. But there is also always a lot of choice with regards to the network structure, like how many layers do we use, how many neurons per layer, which activations function do we use, parameters of the optimization algorithm itself. There's always a lot of properties or parameters which is sort of part of the method, not part of the model structure. And we need a way to figure out which of those parameters is going to be the right choice for our particular problem. And one of the effects of machine learning being based sort of on this complex model structures consisting of relatively simple mathematical ideas rather than some deep theoretical basis like, let's say, system identification, is that figuring out what is the optimal hyperparameter setting for a particular problem is generally very difficult because we don't have this theoretical basis to support decision making here. So this tends to be an experimental procedure where you just have to try different combinations until you find something that works. And with experience doing this comes sort of an intuition as to what works for different problems. There have been papers trying to argue sort of rules of thumb how to set things like number of layers needed and the size of each layer with respect to each other. But in general, it's very difficult to come up with such guides that actually work. It usually comes down to manual work, tuning, retuning, experiments. But doing that, we need some sort of systematic way of testing different configurations against each other. And from a sampling perspective, it wouldn't be right to use the training data to compare these different hyperparameters, as they are called, sets of hyperparameters. So instead we want to have a separate data set which we use to perform a test on a new set of hyperparameters. So the way this works is that we select hyperparameters, we train our network, and then we use the validation data to do a test of the trained network. And then we see the performance of that specific set of hyperparameters on a brand new set of data which was not used in the training. And that simulates the effect of exposing our trained model to new world data, so independent data sets, new information which the model hasn't seen during training. And that gives sort of an honest estimation of how good that particular set of hyperparameters is. And the reason we do this is because it helps to prevent this overfitting effect when we use independent data to test our performance. But then once we have tried a bunch of different hyperparameter settings and we came up with something which we feel is going to be the best we can do, then we have to do another test in order to have another honest evaluation of how good is this model actually going to perform out in the real world. And for that reason we reserve a segment of our data which we call the test data, which is actually only ever used once, and it's only used when we are finished with the whole project. Then we do a check on the test data in order to verify how good our trained model actually is. And this data has to be different than the validation data which we use to compare hyperparameters. Otherwise we risk overfitting the hyperparameters instead. So the reason why we don't compare hyperparameters on the training data is because performance on training data is generally always good. We need to simulate the effect of having new data, which we do by having this three-way split of the data available. Now obviously in some experiments data is expensive to come by, and therefore we might have very limited amount of data, and then there are techniques which can sort of mimic the effect of independent data sets, such as cross-validation. There are textbooks which argue that cross-validation is better than having individual independent data sets. But I tend to favor, if we can afford it, if we have sufficient amounts of data, to try to use independent data sets in this way. In my experience, that gives better evaluation, more honest results than trying to mimic this effect by cross-validation. I want also in this talk to say something about overfitting, because that is one of the most important research topics in neural networks, is how to avoid overfitting. And a lot of the things we do in neural networks is specifically to avoid overfitting, because the network structures in ANN tend to be so complex. Then overfitting is something that these structures is very prone to do. So I want to talk a bit here again about overfitting. And what overfitting actually is that when we train a model with a lot of description power, it means a lot of ability to pick up and adapt to patterns in the data. There is always a risk that this complex model will also adapt to things in the data which is just random, because sampling something which is random with a limited number of samples looks like a pattern. And that's what happens when we do overfitting. So if we have something like these red data points here, to our human observer eyes, it's very natural to think that probably a good model for this is going to be the green line here. But we could also do a model like this blue line here. It still fits the data that we have to exactly the same degree. Both the blue and the green model here accurately fits the training data. But if we were to add a new independent sample, let's say here, it's very clear that we would expect the green model to fit that new sample much better than the blue model here. It would be very surprising if a new data point here happened to be up there somewhere. It's more likely that a new data point would be in this region. And for us as human estimators, that's quite natural to see. But for a stupid computer algorithm, there is no way that a computer algorithm can have that intuition. So we have to provide that intuition by using this generalization or regularization techniques. So something like this blue line here, that's a typical example of an overfitted model, which has adapted to some random patterns in the data, and therefore will give very poor prediction performance on new independent data, simply because those random effects, which looks like a pattern because of limited samples, isn't really a pattern. So when there is new data, those random effects will look completely different and therefore provide poor prediction results. So how do we prevent overfitting, or indeed underfitting, which we talked about in the previous introduction video? Well, the simple answer to that is we have to choose our complexity in a way that is balanced. So we talked about before that when we have an underfitted model, that means something in this region. So that's a model which is not complex enough to describe the patterns in the data. That would be over here. Then we have a large bias error. But when we have a model which is too complex, then we would be over there where the variance increases because of this effect of fitting random noise. So what we actually want is something in this middle region here, where the combined total error is at its minimum. Now with something like neural networks, this is sort of tricky because almost all neural networks tend to be on the sort of high complexity side. So a way to sort of mimic the effect that a model is less complex than it actually is would be to not utilize that complexity to its maximum extent. So we equated before model complexity with description power, which is where the overfitting problem comes from, that we have so much description power that we learn to describe randomness. But to limit that effect of description power, we can simply limit the amount of training that we do. So if you have a neural network which is very complex, it starts out completely random, which is sort of a low complexity model because it hasn't learned to use its complexity yet. But if we are careful about how hard we train the neural network, we can also, by limiting the training, we can sort of obtain this balanced complexity point. That's something you will see very quickly when you start to train neural networks, that if you train beyond a certain point, when you then do your validation and your test data set experiments, you will see that the arrow goes up again. And that's this effect here. That's one of the reasons why we have this three-way split of data to detect that this increase in error happens. So another topic which I want to discuss in terms of training of neural networks is something we call transfer learning. This was actually an idea already published in 1976, which was recently sort of rediscovered. It was in 2016 argued that this might be the next driver for machine learning success. What transfer learning is a sort of a general concept, not really unique to ANN, but that's where it has found its recent uses within neural networks. And the idea is that we can take a model that has been trained for one specific task, and then we can retrain it for a similar task. And this, of course, mimics the way humans learn. We can learn from one particular subject domain, and then we can transfer that knowledge into another subject domain which is similar to the first one. So we don't learn everything from scratch. As a simple example, if you have learned to drive a car already, then driving a truck or a motorbike is going to be much easier for you than if you have never driven anything, because a lot of the same concepts apply. It's just two different subjects which is similar in some way. So that's how we function, and therefore it's something that we wish to mimic in machine learning. And a mathematical concept from this was already available in 1976, but it has found a lot of popular use in recent years. In particular, this ResNet structure, or UNet, which is a very popular example of this. This is a neural network, or actually several neural networks, which is huge. The biggest one, I think, is something like 120 hidden layers. So it's a super deep learning. And this neural network was trained to classify objects in images on a very large data set of millions of images. And this has the effect that this neural network is able to recognize a lot of different objects, but kind of poorly. If you try to use this ResNet as is on any image, you will see that it makes a lot of mistakes. It's not very good at actually doing anything other than just classifying objects. But it has sort of learned this concept that an image contains objects, and then it can be, and this knowledge that it already then has built into the structure of these pre-trained neural networks can then be utilized to learn to recognize a smaller set of specific objects that we are interested in. And that's this transfer learning process, that we take these pre-trained, very complicated, large neural network structures, and we retrain part of it, usually the last layers. We retrain those on a specific smaller set of data. And that makes us able to work or do machine learning with a much smaller data set. So if we wanted to create a neural network from scratch, we probably need thousands and thousands, if not millions, of images of whatever it is that we are interested in recognizing. But doing transfer learning, we can get away with a much smaller data set. And that, of course, makes the whole training process cheaper, as the cost of machine learning in general, the labor of machine learning in general is the data collection. It's gathering the data and organizing and structuring your data. Running the algorithms is usually very simple. Tuning the hyperparameters is also a bit of work, but the main cost, the main workload is collecting data. So by using transfer learning, we can sort of cheat a bit, because we use something that has been pre-trained already on something similar to what we are trying to achieve. Of course, that assumes that there is available a neural network or a model that has been pre-trained on something which is relevant for what we are trying to accomplish. But especially for the very complicated task of object recognition in images, this idea of transfer learning has been used with great success. So before we move on to looking at different types of neural networks, neural network architectures, I want to give a challenge to manually try to fit a very simple neural network to a constructed data set. Of course, this is not sort of a natural thing to do with neural networks. We normally do this thing by computer, but it's still as a learning exercise to understand what the neural network actually is and how it works. It's useful to try and get the feeling for what's involved in configuring or training a neural network to fit a particular set of data. The data in this case is the exclusive OR function, which is expressed in 1 and -1 rather than 1 and 0, because that's more natural for neural networks, if you remember from how activation functions work. The exclusive OR function is given by these 4 data points here. So we have if 2 inputs x1, x2 and 1 output y, and if both inputs are -1, we wish to output 1. If both inputs are 1, we also wish to output 1. But if they are different, 1, -1 or -1, 1, then we wish to output -1. And this can be represented graphically, where we have x1 in blue and x2 in yellow. And then we see that the red values, which is y, is given as 1 here, -1 there, and -1 there. In order to accomplish this, we need a network with the sign operator, just because that's the easiest thing to do by hand. And then we calculate this with 3 neurons. With 2 inputs, that's 3 parameters per neuron in the hidden layer, and 3 parameters in the output layer. So please try yourself, stop the video, try yourself to find these 9 parameters such that this network, given inputs x1, x2, produces the correct output y. The solution, of course, there are infinitely many solutions because the neural networks are scalar, continuous number space, and this is just a few discrete data points. But that is actually part of the learning exercise to understand that for a small data set like this, actually for any data set, it will always be infinite many solutions. So one way to approach this is to draw these 2 lines here and observe that with these lines we are able to, on that line, separate out this -1, that line separate out this -1, so that any value which is above this line is negative, any value below this line is negative, and anything between the lines is positive. So if we then take the space here minus the space here, we get exactly the solution we want, which is 1 in this band up here, negative here, and negative here. And these lines can be described by the training weights here. So this would be the line for neuron 1, which is given by V1, 1, V1, 2, and the bias 1. You can see here that the offset here, 1, would be this one. The offset -1 here would be this one. The inclination of this line is 1, and the inclination of this line is also 1, but inverted. And if we write down the equations for each of these outputs here, y, it would look something like this. So we remember that the neuron actually takes the weighted sum plus its bias. So it would then take, for the first neuron up here, we would take x1 times v11 plus x2 times v21 plus b1 here. Now if we insert these 3 parameters into that equation, and we take these 4 data points here. We see that -1, -1 gives us the solution 1, -1, 1 gives -1, 1, -1 gives 1, and 1, 1 gives 1. Similarly, we can do for the second neuron here, and then the third neuron combines the output of this line and this line, so the output here and here, and combines that into our final output y. And we see that we get exactly the solution here. I hope you try this yourself, and if you got something similar to this or anything else that made this work, then congratulations, good work. It's a useful exercise to understand how neural networks actually function. You get the feeling for what it means, this weighted sum, and also the activation function is involved here, as well as the combination of different neurons in layers and so on. So it's actually a useful worked example, even if it's a bit contrived to do this by hand. Yes, so let's move on to looking at some different neural network types. We mentioned before that the structure is the key thing to making neural networks work in different cases. So most of these types differ in that they use different structures, but we'll go through some of the most used and most common types of neural network structures that's out there in the different frameworks. There are, of course, a lot of others, some more exotic, which we will not cover, simply because it's such a large space of possible neural network types, but these will be the most common ones. So the first one is, of course, the feed-forward neural network, which we have already seen an example of. We even used one in the previous slide to hand calculate the weights. That was, of course, a feed-forward neural network. One can argue that this is the traditional approach. It's the earliest form of neural network, the original one, perhaps, one could say. But it's still a good approach. It's used a lot, and even the most advanced neural network structures today usually have at least some feed-forward layers, sometimes called dense layers, when they are combined with other types of neural network layers. Yes, one good example for the usefulness of this one was the paper Cereson 2010, where they used this feed-forward structure on actual image recognition on the MNIST dataset, which they obtained a very, very good score just using deep feed-forward neural networks without any of the sort of newer, more advanced networks that's typically used on image recognition like this. So it's definitely still has its uses, and it is still the most used network type in the learning setting, at least. Although there are other network types, as we will see, which is more used for image recognition, for example. A version of this feed-forward neural networks can be obtained when we are dealing with the time series data, which is of course typical to the engineering world, where we have usually dynamic systems, so something which has a behavior over time that we are interested in modeling. This is in contrast to the typical case in most machine learning applications, where we have data points that are independent. So we have samples of something, like images, for example. But as soon as we have time-dependent data, that adds an additional challenge to the application of any sort of data-driven modeling technique. But one way to utilize feed-forward neural networks for time series data is to use what's called an autoregressive neural network, or sometimes we add the X, which means that we have an exogenous input. So let's first look at the traditional autoregression, which is of course a modeling technique that is sort of more to the traditional realm and not usually considered machine learning. Depends on who you ask. But the key thing in autoregression is that we try to write a signal as a function of itself. So if we neglect these u's here and only look at previous values of y when we try to predict the next y, that is autoregression. It means regression on itself. And the way it works is that we use these time-shifted samples. So in order to predict yk, we would look at yk minus 1, k minus 2, and so on back to some maximum horizon into the past. So that would be the AR structure. Sometimes we have an exogenous input, which is these guys over here. So that means we have inputs other than previous values of the signal we are trying to predict. Then we add the x here. So just to repeat, the AR structure means that we have a function of previous y's, whereas the ARX structure means that we have also previous values of something else. It can also be multiple values, but then it's another signal other than this one. So one example would be trying to predict the temperature of a building, for example. If we were then only using temperature measurements, that would be an AR structure. But if we were using past temperatures plus, let's say, solar radiation or added electric power from an electric heater, then it would be an ARX structure. In order to do something like this with a feed-forward neural network, we can make sort of a simple modification to our input data. So typically we would have sort of this column here of data where we have sample yk, k minus 1, k minus 2, k minus 3, k minus 4, and from that we wish to predict this k plus 1, k minus 1. So that would be the next sample in each case that we wish to predict. So normally that's the data set we have, just one continuous time series. But in order to get this time shift effect, what we would do is we take this data set here and we take the time shifted representation of this and we add another column, which is basically the same column except it's been shifted one time step. And then we repeat that process, so we have many sort of duplicates of our data set, but always shifted by one time step. And now we use this as our data set, where we have the inputs yk minus 1, k minus 2, and k minus 3. So that would be sort of 4 inputs to our neural network. And then we have our outputs here, which is then the future samples. So it's possible to do something like this, where we have either just one column, so we neglect this, but we predict this one, or we can also use, if we want to predict 2 values into the future. That would depend on use cases, and sometimes we wish to know the values more than one step into the future, which we can also do by, again, having duplicates of these columns shifted forward in time in the prediction part, so the output references. This is just a simple operation in Python, for example, using slicing of NumPy arrays. We can create this sort of shifted columns from the one time series data set that we have. Another perhaps more used version of making neural networks function on time series or something which is sort of dependent samples, like speech pattern recognition, for example, where each sound changes meaning depending on what has happened in the past, is the thing called recurrent neural networks. And the idea of a recurrent neural network is that we want to add memory to the network. That is, we want the network to remember what the previous data samples was in some way, or at least some representation of previous data samples, so that when we predict our sample k, the network already has some memory of what happened in sample k minus 1, k minus 2, some horizon into the past. And this is because it needs to learn what we call temporal behavior, that is behavior over time. It's nothing to do with temperature, it has to do with time. So this is network structures that is based on or designed to operate on time series data. The way this is done is using something called feedback loops, or in some cases special neurons or special layers that has some other form of memory effect built into it. So that gives us a neural network which has internal states. So it's a naturally dynamic model structure, but in the form of a neural network. We can do this in two different ways. One is the finite impulse response network. That is one where the effect of one sample after a fixed number of iterations will die out. This is similar to filtering in digital signal processing. We also have the same concept of finite and infinite impulse response. And the difference is simply whether we have the effect of a sample will sort of die out after a fixed number of steps. So if we just quickly look back to the ARX structure, we see that the effect of something happening to yk here will be, or let's say in yk minus 3, that would be affecting here, 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 here. But at this point, yk minus 3 is not in the dataset anymore. So a change in yk minus 3 up here would be, or here, would be effective here, 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 and then it would sort of fall out of the dataset. So AR or ARX neural networks are examples of finite impulse response. And we can get some of the same effect using recurrent neural networks. So here, for example, is an example of a neural network where we have a feedback loop. So we take something which this layer computes, output it, and feed it back to the same cell in the next iteration. So it's sort of a feedback of the previous output. And this can be done in a way that we limit the feedback to, for example, in this case, only 5 steps. So here we see that the output HT here is unrolled, as it's called, for up to the fifth step, which will then give us sort of a finite impulse response in the recurrent neural network setting. But it's also possible to do sort of an infinite unrolling in a way, where we have the infinite impulse response paradigm, meaning that there is some kind of memory cell which never dies out. If you're familiar with dynamic systems like the simple low-pass filter, that would be an infinite impulse response type of model or structure, meaning that we have the effect of a change on the inputs will be diminished every time step. So let's say we have the output as an input, so the output of the previous time step becomes an input in the next time step times some constant. And then if we do have a change in that output, that would sort of last forever because it's just multiplied with a scalar and then added as an input again. And then that effect, in theory, never dies out. Of course, after some number of iterations, the influence will be sort of tend towards infinity. So infinite impulse response also sort of dies out over time. It's an exponential function. But it is, in theory, always there. Whereas in the finite impulse response, by definition or by construction of these architectures, it actually has zero influence after some fixed number of steps. One example of a recurrent neural network is the long short-term memory, or LSTM framework, which was developed by Schmidt, Huber and Hochreiter in, 1997, which is a framework that was designed to handle speech recognition. And it really revolutionized the field of speech recognition. Prior to LSTM, speech recognition in computers was really, really bad. It was difficult for computers to understand dialects, for example. A country like Norway, where we have a lot of different dialects, made speech recognition, for example, by computerized answering services, almost non-functional, because the computers couldn't understand what people from districts were saying. But in the LSTM framework, it's possible to train computers on data sets and therefore learn to recognize speech patterns, even though the variation in the input data is very large. Another type of neural networks, which is sort of designed for a particular use, would be the convolutional neural networks, or CNN. And this is a type of neural network which has been designed for multidimensional inputs, like, for example, images. So this is obviously not an image, it's just a representation of multidimensional inputs. But up until now, inputs were always a vector. It was just a column vector. But that changes when we have images. It's not natural to slice an image into just one huge column. There are examples of doing that too, where you take the whole image, like each column of pixels, and just stack it on top of each other to a very large input column. There are a few examples where that is feasible, like the MNIST dataset of character recognition, where you expect that the character of interest, or the object of interest, is always in the middle of the image. Then you can sort of do this transformation into from image to a column vector. But in most cases, when we do machine learning on images, the thing or the objects that we are looking for is not necessarily in the same place in the image every time. That's typical case, is that it isn't in the same place. And in fact, the position of the object might not be relevant at all. We just want to know if there are objects in the image, and if so, what are they? So what we want to do is have a neural network architecture which is invariant to the position of the object in the image. And the convolutional neural networks were designed for that purpose, to do what's called feature extraction. So some way of looking at features in images without caring about their position in the images. Yeah. So if we were to do this stacking of columns, to take an image and slice that into a column vector with a huge number of inputs, we would of course get a very large network if we were to do that and run the fully connected setting on an image. So instead of that, we will use this convolution operation, which is more efficient in that case. So the CNN is modeled after how the human visual cortex works, where each neuron works on a small subset of the image. So in the first layer, we will have a neuron which is sort of applied to a piece of the image, looking for features in that image. I will show in 1 second how that works. And an interesting observation here is that the way this is implemented is similar to traditional image processing, where we use masks like this. So a small frame of a few numbers which is passed over the image in some way. This is used, for example, for smoothing images, filtering and so on. If you worked with even manual image processing in Photoshop or whatever, then you've probably used filtering masks in one way or another. And the CNN is kind of using a similar approach. One interesting observation before we show the example is that the weights of these masks, which is our training parameters in the CNN case, are shared between all the neurons. So even though the neurons apply the mask at different points, they have the same weight to that mask. So the mask is sort of constant for the whole layer. And that drastically reduces the number of free parameters that we need to estimate. In practice, we use these convolutional networks in some kind of structure like this. So here we have the input image. We would then use convolutional layers first, maybe with the rectified linear unit activation function, which is typical for this. And then we use a pooling layer, which is sort of downsampling the results of these features. It's combining features from different regions of the images into a more compressed representation. And then we would do convolution on that representation again, now with maybe a smaller cell, because the reduced image information is compressed. And then we would apply another pooling layer. And then maybe finally we have a fully connected layer to do the classification based on these extracted features, which has then been done in two sort of modules or abstraction settings here. And then we have our final output here. So the way this would operate in practice is that we have in our convolutional layer, we have a mask like this, which in my simple example is just 2 by 2, because the input data is just 4 by 4, so it's small. And to apply that mask, we would then have one neuron which applies that mask to these 4 pixels here, and then takes this value mask weight here times this one, this times this, this times this, and this times this, and that gives the value 16. And that's sort of one neuron takes the mask and applies it to those 4 pixels. And then we have another neuron in the first layer over here, which takes the same mask, applies it to these pixels, and gives this output. And then yet another neuron will take the mask, apply it to these pixels, and give this output, and so on until we get this whole sort of feature representation of the image after applying the mask to each different segment. But the mask is the same for all of the neurons, it's just the position in the image which is different. Obviously convolutional neural networks is used with great success for image processing. There are a few other use cases also where they use convolutional neural networks for sort of position invariant data mapping. But it's mainly within image processing that this has been used. And perhaps one of the sort of most typical use cases of deep learning is CNNs applied to images. One example of a partially CNN-based structure is the UNet, which is a fairly recent invention. It's based on, it's a form of residual neural network, or ResNet, which was published in 2016. This paper here is interestingly has over 93,000 references, which says something about the popularity of this framework, and it's used a lot. Yeah, the reason it's called a UNet is simply because of how this shape is constructed. I won't go into too much details, I just want to show an example of a very modern neural network structure based on CNNs. This particular structure is used for image segmentation, which is slightly different than trying to do object classification. So in this case, the structure here is designed for outputting some value which in some way correlates to a particular class, if this is a cat or a dog or whatever. But this case here is designed for image segmentation, which we can see that the input space and the output space is supposed to be not necessarily of the same dimensions, but it's somehow correlated. So what we wish to do here is output a segmentation map, which is kind of a mask above the image, which tries to say, to classify different regions in the image. So rather than saying that in this box there is a cat, we try to find exactly which pixels that consist of the cat or whatever else we may be interested in looking at. And finally, interesting note here is that this structure is combined of many layers of different types. So we have convolution layers, we have something they call copy and crop, we have the pooling layers, and there is some up conversion layers, which is sort of the reverse of pooling layers. And I think there is also some dense feed-forward layers in here, but I'm not sure. But the point is that it's rather a complex structure, a lot of different operations happening together. And it just shows where we sort of are now with the neural network architecture, that it becomes quite complex structures, but it's still based on the same principles that we have discussed so far, with either recurrent neural networks, convolutional neural networks, dense feed-forward layers, plus some of these more exotic things like pooling and upconversion layers. For the last segment of this video, I want to focus on some applications of neural networks. Now we have looked at the details, how a neural network is constructed from neurons, what it consists of. We saw in the previous segment several different types of neural network structures, of which of course there are many more. And now I want to look at some applications to give you an idea of what neural networks can actually be used for. One first example, which is from back in 1992, when neural networks were just sort of starting to regain popularity. It's something called dual energy gamma densitometry, which is a measurement principle that is used in the oil and gas industry. One of the challenges that we face there is measuring so-called multi-phase flow. So if you have a pipe where there is both oil, water and gas, three different substances in one pipe that can travel at different velocities. You want to measure the volume inside the pipe, how much of each of these three phases there are in the pipe. This is a very challenging measurement problem, because this is sort of dangerous substances. You don't want to expose them to open air unless you have to, and you also don't want to disturb the process. So ideally we want a non-intrusive measurement principle, that is something which can work from outside the pipe. And one particular way we can try to do that is using gamma radiation. So we know from physics that these three different materials or phases have a different attenuation of gamma rays with different frequencies. So if we radiate gamma radiation through the pipe, and then we measure the number of photons that makes it through the pipe using photon detectors, then we get kind of a frequency data set, which we can show as a spectroscopic data like this. So this would be the frequencies or the photon energies, and this is the count in the vertical direction, and this is the time direction, so it's multiple samples. And as we can see, this is very noisy data. There's a lot of random fluctuations and variations in these photon counts, which means that we need some kind of data-driven modeling architecture to make sense of the frequency count, or the number of photons for each of those frequency bins, and try to interpret that as a volume of oil, water and gas from within the pipe. And this is something which was attempted by Bishop and James back in 1992, where they wanted to do both a classification, which was classify based on gamma densitometry how the different phases were distributed in the pipe. And we know from physics that there can be many different forms of distributions, like stratified, where everything is in separate layers. It can be annular, where you have gas in the middle, then oil around and water at the edges, or inverse annular, or we can even have homogeneous, when all the three phases are mixed together. But they also wanted to estimate the volume fractions, so how much is it of each of those different materials. One very interesting point, which is made very clear by this article, is that they spend quite a lot of time discussing their measurement principle rather than just focusing on the neural network architecture and the training of the neural networks. And we can see here that in order for this to have any sort of chance of working, we really do need to understand the physics of the problem and the sensor principle that we are trying to use. So if we were to just radiate gamma rays through the pipe in the vertical direction here, and if we happen to have a stratified flow scenario like here, we would see that the top sensor would only see gas, the middle sensor would only see oil, and the third sensor would only see water. because of the densities of the materials involved. That's how they distribute in the stratified flow regime. And therefore we see that from understanding the physics and the sensor principle, if we were to only use vertical beams, then we simply would not have sufficient information in the data to estimate the volume fractions. The best we could do then is to say that the gas is somewhere between here and here, the oil is somewhere between here and here, and the water is somewhere here and here, gas between here and whatever sensor is not measuring gas. So it would then be a sort of a very coarse, discrete data set. But in order to get continuous volume estimates, we actually need these cross beams as well, so in the vertical direction, not just the horizontal direction. So this shows this very important point, which we try to make clear also in the introduction to machine learning video, that in order to do machine learning successfully, we really need to understand the physics of the problem that we are working on and the measurement principle. So you have to ensure that the information that you are looking for is in the data to begin with. And in this case, that means designing a sensor principle that can work in all of these different flow regimes. But it's also interesting to note that even though you do have to use this understanding of the physics, the actual model that was trained in this work doesn't use any physics. There's no fluid mechanics or anything involved in modeling this spectroscopic data in order to transfer photon counts into volumetric flow rates. It's just data-driven modeling, but it's using physics and understanding of the problem in the design of experiments to make sure that the information you need is in the data in the first place. So another completely different example of a use case for neural networks is something we call an autoencoder. In many cases, we wish to represent data in a compressed form. Can be for transmitting over limited bandwidth communication channels, or storage, or some other application. There's lots of situations where we wish to compress data. It can be for interpretation, for example, that we wish to do some kind of classification on the compressed data structure. And neural networks has an answer for how to do that also, which is the autoencoder. And in this case, we do something which is a little bit special. We do a training where we have input and output data to be exactly the same. Normally we have one input set and one output set, but for an autoencoder, the output should be equal to the input. That's the goal. So the error function that we discussed previously would be the difference between the output and the input. And the structure, as we have mentioned many times now, is key to neural networks. And what makes autoencoders function is that we have this gradual reduction in the height of the layers, and then the same gradual expansion in the layers to get back to the output. So it means that in order for the output to be equal to the input, the most important information has to be passed through this thin, narrow hidden layer in the middle here. And that requires compression of information. So whatever information we have in the input layer has to be compressed down to a representation of the outputs of this narrow layer in the middle here before it's expanded again to become equal to the output. And for this to work, we require to do, the network has to do feature extraction to extract the most relevant features and compress those into a form which can then be recovered by the second half of the structure. So this is actually an example of using neural networks in the unsupervised learning paradigm, where you have just one data set. So this is trying to, in an unsupervised way, find the most important features or structures in your data set and compress those into some sort of minimal representation here. Another interesting example of neural networks, which has also been very popular and successful, especially in just the last couple of years. There's been a lot of discussions and work on this type of application, which is the generative adversarial networks, or GANs for short. And here we have a setup where we use two different neural networks. We have the generator neural network, which tries to, based on some random number, generate a data sample. So for example, it can generate an image. And then we have a set of real-world images here. And then we have a second neural network over here, which tries to guess whether the input is real or fake. So it tries to guess if this is a real image or a generated image, for example, or data point. And then if it's successful, then that's a positive for this one. If it's not successful, then that's a positive for this one. So it increases or reduces the loss for the generator function if the discriminator fails to guess or accurately estimate if this is a real image. So it means that we have these two structures sort of competing against each other. One is trying to generate increasingly more and more realistic images in order to fool the discriminator, but at the same time the discriminator network is also trained to separate the real from the generated. This is used for many different things. It sounds a bit weird, like it sounds a bit like an academic idea to try to get two machines to compete against each other. But actually, this has a lot of real-world use cases. For those of you who are Star Wars fans and follow The Mandalorian, you know that in the, maybe this I should say spoiler alert before I put this slide, but I guess everyone knows by now. Towards the end of the season, there was an appearance by Luke Skywalker in the form of a young Mark Hamill, which was of course CGI, because Mark Hamill doesn't look like this anymore. And the way they used, or the way they created a younger version of Mark Hamill was using something called a deep fake, which is actually a GAN application. Deepfakes has been used in a lot of other applications too. I'm sure, yeah, I'll get back to those. The academic research on this consists of an early landmark video rewrite application from 1997. That's when they started to look into the deepfake applications already back in 97. It wasn't called deepfake yet. There was a very interesting Synthesizing Obama program, which was published in 2017, which was also a deepfake application. And actually the name deepfake, interestingly, comes from a Reddit username. There was an actual user there called Deepfakes who sort of invented this term, which has since been adopted by academia and media in general. So it's a fairly recent nomenclature that we call this deepfakes. The academic origins is the GAN, where we try to generate images in order to fool another network, and by effect also fool a human observer. It's still a very active research field, and one of the problems that we are struggling with now is the generalization effect, that we want to be able to generate deepfakes more efficiently, because currently we need quite a lot of input images of the person or the object that we wish to make a deepfake of. There has been a lot of commercial uses for this, like the Luke Skywalker. But there are also perhaps uses beyond entertainment for using deepfakes. But the most typical use case of this is sort of image construction in CGI. One interesting thing here, though, just as a final note, is that it shows one of the interesting properties with machine learning is that it's so accessible. So when Industrial Light and Magic, I guess it was, who created the original CGI of Luke Skywalker for the Mandalorian TV series, some people were not happy with the CGI results. So a guy called Shamooks, he went on and made his own deepfake version of Mark Hamill, and then sort of superimposed that on the Mandalorian video clips. And the IL company were so impressed with his work that they actually hired him. So based on available sort of frameworks out there in the machine learning world, one user was able to do better than an entire company who specializes in movie effects and CGI. So I think that's an interesting thing about machine learning, that it's been sort of democratized in a way. It's something that everyone can do, and can maybe do better than the leading experts of the field. Of course, there are ethical issues of this. That would be an interesting discussion point, because it's, I mean, faking Mark Hamill for video, everyone knows that this isn't Mark Hamill, it doesn't look like this anymore. But the synthesizing Obama program, for example, could be used to detrimental effect to politics. And there are examples also where deepfake problem or deepfake technology has been used to ethically dubious goals. I mean, if you can deepfake anyone, you can basically make anyone say whatever you want. So it's an important research objective also to build this discriminator part of the GANs, so that we can actually detect deepfakes. That is a very useful application as well. Another use case of or neural networks on images, which is also kind of GAN based, at least in the next slide it will be, is something called or image manipulation. So very often when we take images, we have to deal with images of poor quality. For example, if you are taking images of something that is outside, then you have to deal with weather exposure, varying sunlight conditions and shade. Can be fog, can be rain, can be snow, and so on. Which means that you need a very large, complex data set, which covers all of these different variations in weather conditions, for example. As we discussed before, in order to do machine learning successfully, you need a data set that covers all the different scenarios that you are interested in doing prediction under. So if you want to have a system that works in all weather conditions, then you need training data from all weather conditions. That can be very labor intensive to achieve. But one way that machine learning community has come up with sort of trying to remedy the situation is using something that Jeremy Howard termed crapification, which was, he is the founder of this Fast AI, which is a very successful framework for doing machine learning on images, Python based. And the idea is that if we can, using some sort of prior knowledge, like physics description of rain or snow, or at least a description of what it actually looks like on an image, we can take the images that we do have without rain or snow or fog or bad light conditions, and we can make our images worse in a way that is representative of how they would look under different weather conditions. So we can do this crapification process by making images deliberately worse than they really are, and then reusing the same image over and over again with this crapification applied to the image in different ways. So from this image, which is actually pretty good quality, we can change the light quality, we can flip the image, we can flip it that way, we can add shade here, maybe even more shade. And as by virtue of this crapification process, we can then get maybe 8 or many more training images out of our one original good image. So this is a way to improve the richness of training data, which is very important for a neural network application. Another interesting thing here is that since we since we know the original image when we do crapification, we can also use this technique to undo crapification. We can have a neural network which is given the original image as a reference, and then all of this as input data. So it will then try to construct from these crapified images, it will try to reconstruct the real image. And that can be used to also then undo naturally crappy images. And one important use case for the last scenario, where we have this reversal of crapification, is the so-called upscaling technique, which has been done before in sort of traditional photo manipulation, which means that you have an image with some limited resolution and you want to improve the resolution, which is just increase the resolution. And up until a few years ago, the paradigm was that this is not really possible, because you are then trying to have more pixels in the output image than the input image. And with traditional methods, the only thing you can do then is sort of interpolation. And since you don't add any new information by doing interpolation, you're just sort of guessing what's between the data points you do have. The output tends to not look very good. So in the left here you have an example of an upscaled image with Photoshop. And this is taken from this link here, Gigapixel AI, which is a company that delivers software that does these upscaling things. We see here that this interpolation tends to make the image look blurry. And the reason for that is it's not adding any new information, it's just sort of guessing what the pixels in between should be. But a better way to do that is to take high resolution images and then downscale them, and then use the sort of machine learning idea of taking the downscaled image as an input and the original high resolution image as an output, and try to use the machine learning in a way to build a knowledge model that is better at guessing what should be between the low resolution image pixels. So it's kind of the same idea of injecting new pixels between the ones that's in the original image in order to have a higher resolution. But we are doing it in a slightly more clever way, where we have an actual neural network model that contains some knowledge that is useful in order to guess what those pixel values are, in much more successfully so than using pure interpolation. That's what's actually being used here. So it's clear that the image on the right side has much better image quality than the left one, even though in both cases it's been exposed to a 600% upscaling. So it's increasing the resolution 6 times. But yeah, so as we have repeatedly stated, there is nothing in machine learning which is really magic, even though in this case it kind of looks like that. But this information about what those pixels in between the original reduced or low resolution image should be has to come from somewhere. And that knowledge comes from the neural network. It's been trained to guess what those pixels should be by observing a whole database of other images which then exist in both a low and a high resolution copy. So it's a reversal of crapification in a sense. But this case, crapification in the form of downsampling good high resolution images and then reconstructing them. So now we have looked at some interesting applications of neural networks. We have looked at a lot of different structures. So now it's time for you to think about what other applications you know of neural networks. There is a vast number of them, of use cases for neural networks, speech recognition, self-driving cars, to name a few. I want you to write a list maybe, think about what have you encountered today. And you will quickly realize that neural networks by now is everywhere. This is not a theoretical discipline anymore. It's something which exists everywhere. It's used in security systems, it's used for fraud detection, it's used in, as we have seen, applications of different kind. And neural networks and photo manipulation or image detection classification schemes has become so good and so easy to use that it is really now a technology which is available to everyone. That's happened just in the last few years, which is one of the reasons why machine learning, and in particular machine learning on images, is such a popular research field. So in conclusion on this video, just a brief summary or takeaway message. As we have seen, neural networks and deep learning in particular is a very complex and a very large field. It can be actually an entire education just to get the full overview, in-depth overview of all this. But it is a field which is accessible in the sense that there is a lot of frameworks out there. It is very easy to sort of get your hands on the keyboard and start using this, writing code. In a separate video we will take a look at how to use, for example, Keras on top of TensorFlow to do machine learning on simple data sets. But it's a whole legion of tutorials and guides, both in the video and written form out there. So it's very easy to get into, start to work on this. What I think is important is to keep in mind that there is a lot of knowledge and theory behind all those frameworks. So one of the disadvantages of this availability of all the frameworks is that it's easy to forget what you're actually doing, to sort of miss the understanding part of engineering and just apply the things that the framework gives you access to without really understanding what's going on behind the scenes. And that can be detrimental to success when using machine learning. I think it's important to have an overview and some understanding of what's happening underneath all these frameworks, which is what this video was trying to at least give an overview of. There is a lot of applications and there is a lot of different neural network structures. And of course the key to success is knowing which structure works on which types of data. There is also something which we haven't talked extensively about, is all the different training algorithms. That is, we talked about how to numerically optimize the weights or the parameters given some sort of object or error function. But there are many different algorithms that tries to do this in different ways. That's also part of the hyperparameter set for neural network training approach. And also there are regularization methods, which we also didn't discuss too much about here. The most typical one, of course, is use a lot of data. That's the best regularization you can do, is just have a diverse data set with lots of variations. But in the cases where you have limited data, you may have to do other regularization techniques like weight limiting or so on. But that will be a topic for a different discussion. And finally, neural networks is a very active research field. There is lots of new ideas coming out all the time, which makes it a very interesting field to pay attention to. And there is still much to do. It's a very active research field. So for those of you who are thinking about an academic career and want to go into research, there is still plenty of things to explore within the neural networks paradigm. That's what I had for this video. I hope that after going through this video you have now an overview of neural networks, the different structures that's available to you, different key topics within neural networks and deep learning, and that you have some understanding of how neural networks function on the basic level. And that will help you to explore further on your own using all those frameworks which is available out there.